Hello everyone. In this lecture, we will discuss transportation problem, its introduction about this problem and its mathematical formulation. So now look at this example. Here, suppose you are running a factory and suppose you have production units at different locations, and in the blue color, suppose these are the locations of your production units. Say this one is the source S1, this one is the source S2, and this one is the source S3. And in the red color, suppose these are the destinations where you have to supply your product. Say this one is D1, this is D2, this one is D3, this one is D4, and this one is suppose D5. So these are the destinations where you have to supply your product. Now it may possible that demand is something different from the supply of S3, and similarly, so these demands depends on the capacity of the sources and destination. So supply may be different, demand may be different for at each source and destinations. And you know the supply of each of the unit. Similarly, you know the demand of each of the unit. For example, suppose the supply of this S3 is 100 units, demand of D1 is say 50 units. Similarly, say supply of S1 is 150 unit, demand of D2 is say 70 units. So in this way, you know the demand and supply of each of these units. One important thing is there, whenever we are discussing this problem, we generally assume the problem is a balanced one. Balanced means total demand must equal to total demand. Total demand must equal to total supply. So if it is not the case, then we have to add artificial source or supply, which we will discuss later on. Initially, we are assuming total demand is equal to total supply. Now, you know the per unit transportation cost from each source to each destination is also known to you. And the problem is to find number of units from different sources to different destination should you supply so that the total transportation cost is minimum. So what we have to find the number of units from different sources to different destinations we should supply in order to minimize the total transportation cost. Now look at this. This is the graphical representation of this transportation problem, but we need mathematical solution. That's why we convert this problem the form of a table. So here I have written generalized transportation problem where m sources are there and n destinations are there. The C11, C12, so Cij, you can write Cij. This is the transportation cost, per unit transportation cost, per unit transportation cost from ith source to jth destination. So these are the costs. Now look at this A1, A2 up to M. These are the supply. A1 is the supply of source S1, A2 is the supply of S2, and similarly EM is the supply of SM. Similarly B1 is the demand of D1, B2 is the demand of D2, and Bn is the demand of Dn. As I already told you, we are considering the problem a balanced transportation. Balanced means total demand equal to total supply. So you can assume A1 plus A2 plus up to AM this equal to B1 plus B2 up to Bn. So in this way you can say this problem is a balanced transportation problem. Now what you have to find? We have to find the number of units from different sources to different destinations. So you can assume let Xij is the number of units. the number of units supplied from ith source to jth destination. Ith source to jth destination. It means here you can write x11, here you can write x12, here you can write x1n, and here you can write x21, x22, x2n, here xm1, xm2, and xm. So these are the units from different sources to different destinations. Now, how can we write it as a problem of, in the problem, linear programming problem? So for this we have to write the objective function. The objective is to minimize the total cost. So you can write minimize, z, just leave it. You can write minimize z, this equal to minimize z, this equal to, now look at this, you can write x11 into c11. C11 is the per unit cost of transportation from S1 to D1, and number of units x11. So you can write x11 c11 plus x12 c12, and similarly you will move from this column to this column, and up to last you will write up to this column x mn cm. In short, you can write it sigma I equal to I for row m, sigma j equal to 1, this is for number of columns, say n columns. So x I j c I j. So this is the objective function, minimize z. Now what are the constraints? The constraints are two types of constraints will be there, one for different sources, another for different destinations. The constraint for sources are is total supply must equal to even. So for first you will write sources, for sources, constraint for sources. So you can write x11 plus x12 plus x1n, this equal to even, and similarly you can write x m1 plus x m2 and up to x mn is equal to a m. Similarly you can write constraint for destinations. Destination means for each sources the demand must equal to B1. So look at this is x11 plus x21 plus up to x m1, this equal to B1, and similarly you can write for this one x1n plus x2n plus xm, and this equal to Bn. These are m equations, these are n equations. And finally non-negative restrictions, you can write xij greater than equal to 0. So in this way you can formulate a transportation problem into a linear programming problem. This is the objective, these are the constraints for sources, these are the constraints for destination, and this is the non-negative restrictions. So in this way you can convert a real life transportation problem into mathematical or linear programming problem. The solution of this will be, we will discuss the solution later on in the next lectures. So I hope that you got the concept of transportation problem and how can we formulate a transportation problem into a mathematical problem. Thank you.